Hello and welcome to ICDD's InSession webinars. Soon you will hear Professor T.N. Guru Rao present all you wanted to know about polymorphism but were afraid to ask. Please remember to visit ICDD.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
So let me start by telling you about the issue associated with polymorphism. When we talk about polymorphism, it essentially means many forms. So when we say poly, it is many, morphism is forms. So it sort of encompasses almost all branches of science and technology. And this is where the issue comes up. And there'll be a lot more questions because it's sort of ubiquitous in all possible areas of science and technology. And that's the reason why I thought that I will, as I listed in the synopsis as well, that I will go through a few questions and try to answer those questions one by one, clarify the issues associated with those, and then get on to the definition of polymorphism, which itself is going to be having several forms. And this is where the issue comes. It depends upon which area of science and technology we are dealing with. And then once we have that idea clear in our mind, we will concentrate on molecules, crystalline forms, and of course, solid forms in general, including amorphous forms and so on, and then go into the applications, which are essentially associated with the area of pharmaceutical sciences. So it is essentially for the pharmaceutical scientists towards the end of the talk that these questions will be answered in which they were afraid to ask, I believe. So the next slide tells how I'm going to proceed by considering each and one of these areas and explain these areas in such a way that we have an idea. So we talk about origin of polymorphism to start with, and then we discuss types of polymorphism and identify these types of polymorphism. We then talk about theories based on physical and chemical reasoning for the formation and give some examples to illustrate the formation, and then discuss the impact on industry in general. So this is a basic outline. I may be going back and forth among these areas, but there are three questions anyway. What is polymorphism? How polymorphism occurs in nature? And then the third question, why? The third one is the most difficult one to answer as we will go along, and we will see how we approach the problem in various ways. We can approach from theoretical basis, we can approach from experimental results and so on. To begin with, let me put polymorphism as it belongs to different areas. As I have written at the bottom here, it is the same wine in different bottles. So as for definition of polymorphism is concerned, it is the existence of a given material in very many forms. It is the same material and it can exist in different forms. For example, in biology, we can talk about different phenotypes. We can talk about sexual dimorphism, lipid polymorphism, nuclear dimorphism, etc. Essentially, this sort of covers starting from the fundamental element in which biology is involved to molecular species, where biology becomes a very important concept, and then extend the molecules to various assemblies of these molecules in cells, membranes, cytoplasm, etc., etc. And in all these cases, we do come across polymorphism. This is where the issue in biology is quite complicated, and polymorphism is discussed in an entirely different sense than what we will discuss today towards the end of this discussion. I will probably come back to biology and try to see whether we can put some kind of a correlation between what we have learned now and then biology, how we were going to apply. The other area where it is ubiquitous, as I mentioned, is the area of computer science. Here we have data of different times, and they all exist with the same interface. So it's a question of how the data now gets assimilated and accommodated into various scripts. JavaScript is one such example, and computer science therefore has a general behavioral tendency towards polymorphism, and that is an issue which bothers and at the same time also helps in the development of computer science and technology. We will approach the problem slightly differently. We will go from the very basics. We will start from the elements in the periodic table and then see whether the elements in the periodic table like carbon, sulfur, and so on in their solid form, do they exhibit polymorphism? Indeed, they do exhibit polymorphism, and this property is referred to as allotropism. And these are the allotropes which we are very familiar with from our school days. However, there are lots of issues even in these, as we will discuss further. And then I will go into molecular species and take inorganic materials as examples to start with, but I'm not probably going to have time enough to go into the details of inorganic materials. So maybe we may have to skip it. However, we make a statement here that inorganic materials were the first to be identified and discovered to possess polymorphism. The crystalline forms of calcium carbonate, calcite, laterite, and aragonite were characterized way back in 1788. This started off the understanding and appreciation of polymorphism in inorganic materials, and several inorganic materials with different physical properties and sometimes even chemical properties there, which we will have to worry about in case of inorganic materials, particularly in zeolites and so on, where these property of polymorphism becomes an issue. When we come to organic and organometallics in the solid state, the earliest known example is benzamide. In 1832, the polymorphism in benzamide was discovered. So it is, as I mentioned, it's the same wine in different bottles in different areas of science and technology. And this is where there are questions which come up. And sometimes we may be afraid to ask, mainly because it looks like we should be knowing this, but we have not learned about it. And that is why we hesitate to ask questions. And that's the reason why I gave this title. It has nothing to do with the fact that at the end of 45 minutes, I guarantee you that you will never be afraid of polymorphism. In fact, you will see that we will be afraid of polymorphism more and more, particularly in pharmaceutical industry. And let us start from looking at, as I said, at the very basic elements in the periodic table. We will go to the element, which is where we are all familiar with, the allotropic forms of carbon. This is diamond, graphite. It is single layer graphene, of course, is a recent identification. Diamond and graphite are the two which we very well and thoroughly know. Diamond is the sp3 hybridized state of carbon, where all the four valencies associated with carbon are shared. And in the case of graphite, we have the planar structure with the sp2 hybridization associated with the carbon atom. This we learn in our basic chemistry, and the knowledge here tells us that we have two entirely different solid forms, the allotropes. One is the hardest material, and another is a very soft material. The hardness and the softness depends upon how the structural makeup is made in these two. And this is how carbon now appears in two solid forms. And also it is a terrestrial identification. That means to say that they can be unearthed in the surface of the earth and below the surface of the earth. Obviously, it is clear that diamond, which is formed at very high temperatures and pressures, because we have to bring a well-known four valencies associated with carbon, because it's already saturated enough to make bonds, and as a consequence, make the solid. In the case of the graphite, on the other hand, we have now a planar structure with the available two electrons, which now could be shared, and the planar structure can be compounded. And that is the reason why the graphite is found closer to the surface of the earth at a reasonable temperature and pressure, whereas diamond is discovered way down in mines and so on. But once it is discovered and when it is unearthed, It is a very stable form. Carbon in the diamond form is the hardest substance, and it has all other physical properties which are very different from the physical properties described by graphite. So the same element in two different forms. This is allotropism. In fact, carbon recently has been found to have many more in the last 20 years or so. Many more solid forms of allotropic forms of carbon have been found, which are listed here. The Longtime, Buckminster fullerenes, of course, we are all familiar with this, C60, Z70, C80, and so on. And then there is a very peculiar form of carbon, which is amorphous. And that means it has no crystalline continuous periodic repeat arrays. However, it is a solid material, and amorphous carbon has its own specialized properties. And as a consequence, it gets identified as an entity on its own. Similarly, the recent identification of nanorods. So these are the allotropic forms in one element. You know, we have a periodic table of so many elements, and one element, carbon, shows this. You are all aware that sulfur shows many, many forms, but I don't think we will go into the detail of it because we will be running short of time if we keep on discussing only these aspects. So let's go further and look at some compounds. And I thought one of the very interesting things, in fact, I wanted to put a picture of picture of chocolate over here, I forgot. But then the 6 polymorphs of cocoa butter has been identified. Cocoa butter is the basic product in making chocolate. And it is very interesting to see that these forms exist in a very short temperature range. Remember, diamond and graphite existed at 2 very different temperatures. The melting point of diamond and melting point of graphite are very, very different. They are distance far apart. On the other hand, here, the melting point of each one of the forms of cocoa butter vary from 16 degrees to 36 degrees centigrade. And it is found that each of these forms are therefore continuously converting from one to the other at a given temperature, their own temperature. And so it is very important that one should have a suitable melting point and good stability during storage in order to make a good chocolate. And this is a challenge in chocolate manufacturing industry. So the selection of the appropriate crystalline form becomes an issue. And it has been very many times demonstrated that form 5 is the best choice. 34 to 35 is the melting point. So you bite chocolate, it melts in your mouth. And that's the way in which cocoa butter is now made into chocolate. So you see that the polymorphs associated with this solid material, cocoa butter, has these kind of physical properties. And the physical properties and the melting point correlate in such a way that we eventually, in the manufacture chocolate, it has to be done in such a way that we have the correct melting point, the absolute melting point, which is required for high quality chocolate. So it's a challenge. And the challenge was identified way back in '66. And it's interesting to note that even now, the best of chocolates do have some small little problems. And so chocolate industry indeed is very much struggling with the polymorphism issues associated with cocoa butter. So one of the things they do is to add additives. And the additives are the ones which kind of stabilize the given form. So therefore, when we are actually discussing polymorphic modifications, we will discuss the issue of adding additives and see whether we can stabilize or generate a new stable polymorph. We will discuss that with examples later on, which becomes very, very interesting. So we start with the possible definitions. We start with the definition of what is polymorphism, the ability for a molecule to crystallize in more than one crystal form. This is a very old slide, but I'm sure you are able to read it out. Chemical identity is the same. It differs in melting points, X-ray diffraction patterns, very crucial. We'll have more and more of this discussed. Dissolution rates, varying degrees of solubility, different morphologies, tensile strengths, and densities. So all the physical properties that are associated with monomorph is to be identified, so that we now are able to distinguish the polymorphic modifications. The best book to read and understand polymorphism, in my opinion, until today, even though there are lots and lots of review articles in recent times, I still feel Joel's book on polymorphism in molecular crystals, published by Oxford University Press in 2002, is, I would say, the real quality textbook which we could refer to in order to understand polymorphism. His contributions to this area has been immense, not just from the scientific understanding and evaluation point of view, but also from the fact that he has been a very important person for pharmaceutical industries, particularly fighting out various cases with industry get into because of polymorphism issues legally. So he was also a legal consultant, and he has done enormous amount of work in this particular area. There are three types of polymorphs that are identified. One is referred to as the packing polymorphism. The other is the conformational polymorphism. The third is the pseudo-polymorphism or solvatomorph. The third one is something which is a bit of a puzzle. Whether we could call it polymorphism or not depends upon whether we have the presence or absence of a solvent. The solvent could be hydrate, of course, water, or any other solvent with which the crystallization occurs of that particular solid material. So these are the three types of polymorphs which we have to distinguish from each other. And these polymorphs essentially are characterized by the existence of different unit cells as far as the crystal structure is concerned. Let us look at the possibility of conformational polymorphism. Here is an example of a compound, probukol, with rotation about single bonds in a molecule leading to several possible conformations. So there is a bond about which we can rotate, in this case, this way. Oh, sorry. In the case of a rotation, we go from rotate this bond 90 degrees, we will get into the form 2. Now, these two forms can crystallize separately into two different crystal systems with two different morphologies, as is shown here. So the morphological character, the behavior under the microscope, which we look at, is very different for this form compared to that. So we can identify the conformational polymorphs by this approach. And since it is an involvement of a rotation, obviously the physical properties associated with these two will be very different. The melting characters are different. The behavioral characteristics are different. And as a consequence, these two now serve as polymorphs of each other. The next slide shows an example of packing polymorphism. In this particular case, I have taken the example, very old example. In fact, it's from one of my very old slides of ethyl maltol. It has three different polymorphs. Form 1 crystallizes in a monoclinic space group P21 upon N. And these crystallize as blocks, morphology or blocks. And you see that hydrogen bonding between these two is the one which essentially packs the molecules in the crystal structure. In the previous case, it was the molecule itself which changed its conformation. Here it is the conformation being the same. The packing in the crystal lattice is changing. So the two patterns are different. And this is again a question where some people refer to these very loosely as packing polymorphism. And then we have to ask the question about how this packing polymorphism is coming up. And in that kind of a situation, we have this issue of the packing of the molecules in the crystal lattice. So you see the three lattices are very different. Monoclinic in one case, hexagonal in the other, and triclinic in the third. And the way in which this packing of the molecules occurs is very different from each other. As a consequence, the melting points differ because the melting point now essentially gets rid of these nice arrangement of the packing, and eventually the packing crashes off into a continuous distribution of molecular species, and therefore you see that the way in which these three are packed differently, the melting points are different from each other. And as a consequence, we have, though the molecules have nearly the same conformation, they possess different intermolecular interactions, leading to different arrangements in the crystal. So this is packing polymorphs. The third one, which is rather an issue which has been discussed in literature for over several years, it is the occurrence of what is referred to as pseudo-polymorphism. So when we use this word pseudo, it already looks suspicious. And we can say that it is, in case of hydrated samples like what I have given here, in case of ampicillin, the anhydride ampicillin anhydrate packs this way in a space group P21. And in the case of when water molecules enters and holds the molecules together, the packing is essentially different. And the conformation of the molecule, even though may be very similar, it's not exactly similar again, because water now forms hydrogen bonds and varies the conformation as well. So both the conformation as well as the packing change. And in this particular case, it crystallizes in a space group, which is 2-1-2-1-2-1. So this is a monoclinic system, this is an orthonomic system, and therefore these two are polymorphs of each other. They have different physical properties. Now this is, though not so very characteristic to define a polymorph, because we have now an additional molecule of water or molecules of water. In this particular case, it's 3 water molecules forming the packing in the crystal lattice. So this is a very different compound than this one in that sense, because it has an additional solvate. But then, once we call this a solvate, the physical property is changing, the property of the drug molecule also changes, and therefore issues associated with the pharmaceutical industry, where they are worrying about the stability of the molecule, the stability of the drug molecule in the given crystal form, the preparation methodology, the way in which they tablet the materials and so on. There are so many other factors which essentially facilitates them to use this pseudo-polymorphism as a possibility to get new polymorphic modifications. So solvatomorphism is therefore a very crucial component in drug design, especially when it involves patent rights and so on. So the pharma industry is very excited about it. Whether we can bring it into the definition of a polymorphism or not, we will examine it later on. It's a very question which we are sort of afraid to ask. So we will ask that question and see whether we can sort it out. The next slide shows the reason for all this. You see, we said, why polymorphism? Polymorphism is a consequence of nucleation and crystallization. So when we now make a material into a crystal, we make the material into a crystal by very many ways. One of them is evaporating the solvent in which we keep the compound. The other could be melt the compound and recrystallize the compound. And it could be in any other way, like vapor evaporation, vapor deposition of the compound itself on the surface, and so on. So when several of such operations are involved, the nuclei that are formed with molecules coming together, which follow what is known as the Ostwald's rule, they essentially bring approximately 10 to the power of 20 molecules. We know that this is a very large number of molecules into an array of 3 dimensions. It could be molecules, it could be ions, it could be species associated with hydration and so on. But essentially, we bring 10 to the power of 20 molecules to crystallize. So the process is essentially kinetically controlled. So it is the kinetic way in which the crystallization process occurs is the one which matters. And the chemical reactions, therefore, are essentially kinetically controlled. So these are chemical reactions in some sense, because when the nucleation occurs, the molecules come close to each other. And as a consequence, it's a kinetically controlled phenomenon. In case of supramolecular reactions, when we bring in molecules together and assemble them, they could be thermodynamically controlled, and they hover around the equilibrium. So when we have chemical reactions which now bring molecules together into the crystal system, first the crystallization process occurs, and then the molecular species are brought together. We do have a situation where the control of thermodynamics is also a very important factor. So the crystallization, though kinetically controlled, can also be monitored by variations in temperature, solvents, rates of concentration, impurities, shock, gravity, and so on. In fact, there were lots of experiments which were done in space in order to see whether crystallizations can be affected in different ways in order to form polymorphic modifications. So these are all the issues which actually cause confusion in understanding polymorphism. So at this particular stage, where we have spent some amount of time in trying to see what is polymorphism and how polymorphism occurs and so on, we do see a situation where we are now faced with a problem of kinetics, kinetically controlled thermodynamic reactions. So how do we go about further on this issue? In fact, there's a very beautiful example which occurs, which has been produced in case of 5-methyl 2,2-nitrophenyl amino 3-thiophenyl carbonitrile molecule. When crystallization is affected in different ways, we end up with different kinds of polymorphs. It's a very curious case. This is the molecule, and the molecule has a free rotation. This theta angle represents the rotation, the dihedral angle associated with this single bond. So as a consequence, the rotation is possible about that bond. And as a consequence, it can stabilize the molecule in different forms. And when it stabilizes the molecule in different forms, we end up with different crystals. And it so happens it is very colorful. So this molecule is referred to as the molecule Roy because it is red, orange, and yellow. So you see the red prisms, the orange needles, yellow needles, all these are different polymorphic forms, and we do get different properties. The properties are in such a way that the melting points associated with each one of them is in a very small range. It is between 94 and 115 degrees centigrade. And in fact, the paper in 2000 reports 6 polymorphs, which are shown here. But actually now there are 12 fully characterized polymorphs as of today. In fact, I recently saw that the 13th one has been proposed, but it is definitely to be characterized because experiments are continuously going on to generate more and more polymorphs of Roy. And all these are existing in a very small temperature range. So the interconversion from one polymorphic form to the other is another issue. See, these are the problems in polymorphism. So we tend to understand these. At the same time, we have a doubt in the back of the mind. Is it all clear? Obviously, it is not very clear. In fact, in a recent simulation study, to 2022, a very recent article in Chemical Science, using the so-called method of crystal structure prediction, we will discuss it much later, a few minutes later rather, suggests many, many more possible polymorphic forms. But then one has to worry about variable thermodynamic conditions, variable pressure, variable temperature, and so on. So it is always possible to get what is known as an energy landscape that is associated with a given molecule. So any given molecule has an energy landscape that is associated with it. And in that energy landscape, different kinds of forms can be stabilized. And this stabilization depends upon when the solid decides to form a solid, crystalline form, or an amorphous form, it does not matter. But when they do assemble in that particular form, we do see the character of the given material change, and therefore the physical properties change. In fact, when we look at all polymorphs of Roy, if you look at the methanol solutions, they all crystallize from methanol solutions. Here is the the DSC of the 5 different polymorphs. You see that they're all within a very small melting zone. So one can convert to the other very, very rapidly. Indeed, when the crystallization is affected, the polymorphs come as mixtures, and therefore one has to separate them. The separation is done by repeated crystallization experiments, as we will detail below. And they come as concomitant polymorphs when they are from a supercooled melt when they are crystallized. They come as concomitant polymorphs. We'll see what is concomitant polymorph in a minute from now. So why the yellow form from solution mediated or any other from nearest room temperature? Fast crystallization, if we do, it is favored to form needles. And again, a mixture of orange and yellow. We can separate them under the microscope looking at the color. And although obtainable by heating R, the orange prisms can be obtained only with seeding with the orange crystals. And they tended to crystallize with orange needles and yellow needles. So you see that one is convertible to the other. They all come together, but because of the color variations and the polymorphic modifications, the morphism associated with it, the morphology that is associated with it, helps us in separating these forms. Very interesting compound, very important compound in the sense of trying to see and understand what is polymorphism. So the next slide defines what are co-crystals. Co-crystals are solids that are crystalline single-phase materials. You see, here is another situation where the pharma industry was very much perturbed when people started making co-crystals. So the co-crystals are also solids. That is, we have a pharmaceutically important compound, let us say. It is co-crystallized with another solid, or it could be another compound. So the two compounds now crystallize into a solid form. They become co-crystals. Now, can these be called? Yes, these are, of course, once they become crystalline, they are single-phase materials. And as a consequence, they are new form, and therefore are they new polymorphic forms. There's a lot of discussion, and in the year 2012, a definition to this came up. And the co-crystals are solids that are crystalline single-phase materials. They are composed of two or more different molecular or ionic compounds, generally in the stoichiometric ratio. And then the definition came, which are neither solvates nor simple salts. So therefore, co-crystals can also be considered as possible polymorphic modifications in case they show polymorphism. That's the reason why I have put a question mark. Co-crystals by themselves are new compounds. However, co-crystals, when they do form, they can form in such a way that they can form different kinds of packing modifications depending on the intermolecular interactions in the solid state. And they can describe what is known as a co-crystal polymorphism. In fact, I made a slide from one of our recent work, but I thought of lack of time would not allow me to show that slide and explain the work in that particular piece of a demonstration where we can see the formation of co-crystal polymorphism. So at this moment, you believe me that co-crystal polymorphism is another issue which has to be tackled along. And it is very important. So we now come to the basic definition of a polymorph. With all these, how are we going to define polymorphism? So a polymorph is a solid crystalline phase of a given compound, resulting from the possibility of at least two different arrangements of molecules of that compound in the solid state. This was the definition which was given by Macron in the textbook which he wrote, and in the New York 1965 publication. So in 1965, a polymorph was defined for the first time in a clear way. A polymorph is a solid crystalline phase of a given compound resulting from the possibility of at least two different arrangements of the molecules of that compound in the solid state. So this does not bring in the actual definition that is associated with polymorphs in the context of pharma compounds. We will see that that is required later on. But however, this defines very clearly what is polymorphism. And the best of next polymorph definition came in the IUPAC nomenclature. So IUPAC decided in the year 2009 to define this as a reversible transition of a solid crystalline phase at a certain temperature and pressure, the inversion point, to another phase of the same chemical composition with a different crystal structure. This is a bit involved. It is involved because it talks about a reversible transition of a solid crystalline phase. And this reversible transition means that we can go from one form to the other. It is always, therefore, by definition, possible to go from one form to the other. Is that really the case? Is it that we can go from one form to another, and that particular form is a thermodynamically stable form, and as a consequence, the stability will ensure that that particular polymorph cannot go back to the other form. So this, this kind of an ambiguous definition was an issue. And then there was lots of discussions on this, in particularly when accepting the patent issues associated with polymorph modifications in drug industry. So FDA came up with a definition, and this is the working definition which is now available for pharmaceutical industry. FDA uses a definition for the classification of polymorphs like this: different crystalline forms of the same substance, and it includes pseudopolymorphs and amorphous forms. So this is the publication in 2012, which brought the definition of classification of polymorphs for the first time. I'm sorry about my throat. It is because of the pollution which is coming from outside. I hope I will get over that in a minute. So it uses the, here you see that the definition that is accepted and given by FDA is to the advantage of pharma industry. You can have pseudopolymorphs, you can have amorphous forms, and the question of including co-crystals is still a remaining enigma. So effectively, polymorphism essentially remains an enigma. As I say in this next slide, that polymorphism, the existence of the same chemical systems in more than one crystalline modification, was an enigma at first, then became a curiosity, and more recently, a subject of systematic studies. Extensive studies have classified them into conformational polymorphs, synthon polymorphs, packing polymorphs, isotopomorphism, etc. And their energy profiles have been quantified by theoretical calculations. Essentially, what this definition means is that polymorphism now is no longer an enigma, but a curiosity, which means to say that any given compound must have polymorphism, which is very interesting and very, very questionable as well. Because once we have a thermodynamically stable form of a given material, can it in any way go to the other forms? It can go to the other forms only under certain circumstances, which we will see in a little while from now. And this was the way in which we wrote the themed issue of the editorial note in the themed issue of polymorphism. And then the area of crystal engineering tried many, many things. The group of Desiraju, Zawarodko, Bernstein, Sally Price, and many others, they have written a huge number of articles. They have made several attempts, explanations, how to control polymorphism, crystal structure prediction, whether we can predict a priori the polymorph formation, and so on. All these literature is available. And it is a huge set of literature material, but then the particular article which is required to get one understanding of polymorphism in one single article is missing, is still yet to be obtained. And that is the interest which still remains. So we will now come to a stage where we will have to now characterize these polymorphs. How are we going to characterize them? This is very easy now. We come to the experimental arena where we talk about hot stage microscopy, thermal analysis, spectroscopy, and of course, X-ray diffraction. X-ray diffraction remains the paramount technique but both in powder and single crystal methodologies, which we will use in polymorph characterization. Hot stage microscopy will verify melting temperatures, transition temperatures. It also will tell us about the way in which the crystal habit behaves under the microscope. Thermal analysis like DSC, TTA, and DTA will give us a clear understanding of the melting behavior and the solidification behavior when we go across the melting, forward as well as backward. It tells us the hysteresis that is involved in the transition state. And of course, spectroscopy is a very good support where we can have infrared and Raman particularly, because it will talk about the vibration and the rotational modes. It will also talk about the solid state Raman, will also talk about the correlation that we can obtain between spectroscopy and X-ray diffraction. Now, how do we do this? Now we have to take some examples to analyze that. This is now an essential status where we get into, and we have to analyze this one. This comes from polymorph conversion and stabilization. This now becomes a very crucial step. So we have to worry about how we go from one crystal form to the other. There are what are called crystal to crystal phase transitions, lots and lots of literature again. A particular polymorph has to be characterized with respect to efficacy, ease of manufacture, stability on storage, and transformation to another form on storage or during manufacture. This is essentially for the pharma industry. So I now concentrate the whole issue from the point of view of pharma industry and look at it from the physics point of view. The structural phase transformations are generally characterized by Cauchy-Clapeyron equation. In fact, I had this equation here. It is not showing up. Delta G is equal to T delta S, delta H minus T delta H, where delta G is the Gibbs free energy function, delta H is the enthalpy of change, and T delta S is the temperature and the entropy change. So when the value of G is the lowest value of G is thermodynamically stable. All other phases under the same set of conditions will be unstable. If you want to learn more about polymorph conversion and stabilization, there's a beautiful article by Anwar and Zan in Advanced Drug Delivery Reviews, which I suggest you read and get an idea of how these things happen and in what way the free energy, Gibbs free energy, controls the polymorphic conversion. Here is a simple example. So when the value of delta G is less than 0, transformation is spontaneous. When the value of delta G is equal to 0, the phases are in equilibrium. And the value of delta G is greater than 0, transformation is not possible. See, this is the thermodynamically stable form. But we can always change it with energy input. So we can put energy in different ways. We can have change the pressure, we can change the temperature and so on. And as a consequence, even the delta G greater than 0 can be pushed out. Here is a representation of the energy, Gibbs energy versus temperature. You have shown an example where there are 3 polymorphs, alpha, beta, and gamma. They are shown in this figure. The gamma form will be thermodynamically more stable. The gamma form, which is shown here, is the thermodynamically stable because this is the one which is showing the highest melting, thermodynamically more stable form. So there is a transition temperature T of T. At this transition temperature, the alpha and the beta forms will have the same energy. So they are in equilibrium with respect to each other. So once they are in equilibrium, you see that delta G becomes 0. Delta G is 0 for phases which are at equilibrium. Upon the increase of the temperature, the alpha form gets transformed into beta form spontaneously. So the moment we come here, alpha goes to the beta form. You see that these two are very close to each other. So alpha goes to the beta form, which is the next stablest form, which can be associated with this particular polymorph. So to explain this in a very simple sense, of course, this reference is a very beautiful article again on polymorphism and various issues that are associated with polymorphism. In this short 50-minute talk, it is very difficult to cover all the topics. We are already at 9:18 now in Bangalore, which means I have another 10 minutes to go before I have to end this talk. And so essentially what we have to see here is that in case we have more than one polymorphic form, we have to look at the corresponding Gibbs energy that is associated with it. If the Gibbs free energy is less than 0, the transformation is spontaneous. And if it is equal to 0, the phases are in equilibrium. That means alpha and beta coexist at a temperature T. So you cannot now separate the two forms. They're together at this particular situation at TT. And then alpha goes over to the beta form. However, gamma is the most stable form thermodynamically. So we can therefore have a situation where we have all the three forms, alpha, beta, and gamma, and one has to worry about how we go from one to the other. I just thought that I will spend a minute on talking about enantiomers and tautomers. We have to remember that enantiomers and tautomers are not polymorphs, because enantiomers and tautomers are essentially two different objects altogether because of tautomerism and enantiomer interchange. So they are not really the same material. See, the requirement of a polymorphism is that they have to be the same chemical, same compound, and then the chemistry has to be the same, but they can go into different crystal forms. When we have enantiomers and tautomers, they are not polymorphs since they involve breaking and reassembling of a chemical bond. However, it is to be noted that polymorphism with the same enantiomeric or tautomeric form, it is possible to exist, to get a polymorphism in such case. And this is an example of phenobam, which was identified and reported by our group several years ago. So what it tells essentially is the key technique in all these is the use of X-ray diffraction. And ICDD, with the big amount of data that is available already in the ICDD database, it is very, very critical to use the X-ray diffraction data to the advantage of looking at polymorphic modifications. We can look at the existing polymorphs if we want to make a new polymorph and then evaluate them. X-ray diffraction would aid in all these very, very unique. All solid state pharmaceutical materials can be analyzed by their diffraction pattern, independent of whether the pattern is characterized by coherent or incoherent scattering, writes the group from ICDD. They write this in the practical guide to pharmaceutical analysis using X-ray powder diffraction. This article is highly recommended. This is published in 2019. This covers all forms of solids, which means crystalline and non-crystalline. And that's the reason why they are saying coherent or incoherent scattering. Incoherent scattering essentially is not something which is generally employed in a routine diffraction technique. In a routine diffraction technique, where we have the powder diffraction or the single crystal diffraction, we always use the coherent diffraction data. The X-rays are coherent in all these situations. We have to speed up a little bit. So we will say there are three different forms of cinnamic acid, alpha, beta, gamma. I discussed alpha, beta, gamma just a few minutes ago. So let's take the case of cinnamic acid. This is a very classical example, 1973, organic chemistry in the solid state. This was one of the very first observations where the solution state and the solid state combinations of cis and trans, they could form three different forms depending on the solvent used. In acetone, they form alpha form. In benzene, they form the beta form. And the aqueous ethylene, they form the gamma form. And gamma form shows no reaction between these two. These two show what are known as solid state reactions. There is a dimerization that occurs between these two double bonds. A classic 2:2 dimerization, which occurs and forms a 4-membered ring. It is found to form a centrosymmetric dimer in case of alpha form, a mirror symmetric dimer in case of the beta form, and no possibility of forming this in the gamma form. So the three states in this particular case are different from each other, And so there are 3 different polymorphic forms. Another example which I want to take is from the interconversions of pharmaceuticals. 4 polymorphs of phenylbutazone. They can be prepared by crystallization from different solvents. Polymorph 1 from tertiary butyl alcohol, polymorph 2 from cyclohexane, and so on. Polymorph 3 converts to polymorph 4 under pressure and also spray-diced samples resulting in altered polymorphs. So these are all the observations that are made in the pharmaceutical industry. And obviously, which is the one which has to be the polymorphic form is an issue which has to be discussed in detail. And this article, which has appeared in the Science and Engineering first edition, Pharmaceutical Crystals, underlines the importance of polymorph interconversions. So FDA guidelines automatically are very important. The applicants who apply for this have the responsibility to control the crystal form of the drug substance, and the suitability of the crystal form needs to be demonstrated if bioavailability is affected. Thus, the abbreviated new drug application rules should include the information on solid state properties, especially when bioavailability is affected. This is something which essentially tells us that first, we have to now look at different crystallization conditions. Then we look at the test of polymorphism. Then once we say the polymorphism is discovered or not, if it is not, we ignore it. If it is discovered, we say yes, and then measure all the physical properties, measure the stability of the compound, and then say different physical or chemical properties if they are. Then the composition of the drug substance is analyzed and see whether it gives a single polymorph, which is a qualitative control using DSC and PXRD. And using DSC and PXRD, again, we describe it as a mixture of forms, and that will give us a quantitative control. That means we can have 2 different forms in different ratios, and still it could be an effectively new drug. So the discovery of the drug, therefore, goes through these procedures, and then only it is accepted. Now I come to the last few minutes of the talk, where maybe 3 minutes, where I will illustrate with a few examples from literature how this issue has come up. One of the earliest examples, which most of you know, is the ritonavir and antiviral drug, which gets converted. In fact, in the year 1992, FDA approved, but in 1996, the approved drug failed the dissolution test. What really happened was the Form 2, less soluble and thermodynamically stable than Form 1, and therefore Form 2 got converted to Form 1. XRD clearly illustrates this in terms of these red lines, which refer to the Form 2, and the blue lines, which refer to Form 1. And you see the 2 are very different from each other. Then there is an example which is from ICDD. James Kaduk and Tom Blanton, who are in this audience, I think, today, they studied this compound, and they found that there are 2 types of compounds which can be generated, and these are the polymorphs identified for germachrome. There is a lot of discussion associated with this, and that is referred to in this article. One example from our literature, where I've mentioned at the beginning that sometimes the addition of impurities can generate new polymorphs. One of the very startling examples is the case of tadol. The compound tadol actually crystallizes with in a space group 2121221, shown in this in terms of this kind of morphology. And in the presence of a chiral impurity, we added a small little chiral impurity. We see that the crystallization is found to be responsible. The appearance of the chiral impurity crystallizes in a different form. You see needles. We could separate the prisms from the needles and study their crystal structures. We see that we did generate a new polymorph by addition of a chiral impurity. Now, if this particular chiral impurity is an advantage or a disadvantage in pharma industry can be found out by studying the solubility and other related properties. There's another example which I'm going to skip, but come to an example which is probably the last example, last but one, where we actually took a liquid This is an example of diphenyl ether where we crystallized the compound in a capillary in situ on the diffractometer. And the way in which was the crystallization processed, one is a rapid cooling from the room temperature to very low temperatures, and repeated rapid cooling and heating generated one type of crystal. And then the other one was a slow cooling rate, and that slow cooling rate resulted in a different crystal structure. So we could generate the polymorphic forms, alpha and beta, as we call them here, 1 and 2. And the two packing motifs are essentially changing in terms of weak interactions involving CH pi. This is, in fact, the first example of a solvent demonstrating to have polymorphic modifications. The other example is the third polymorph of phenylacetylene, which we looked at, where we essentially see the pathway of crystallization. So this work shows that to some extent, the crystal structures of polymorphs with higher values of the number of molecules referred to as Z prime may provide some clues as to how lower Z prime forms evolve during crystallization. So when crystallization occurs, large number of molecules, 10 to the power of 20 molecules come together, and these molecules now form assemblies, and these assemblies will follow certain rules, which are essentially nucleation followed rules, and those rules probably are verified or probably are violated, depending upon the conditions in which we do the crystallization. So from an assembly of a very large number of Z prime values, we can arrive at properly arranged Z prime values. By Z prime value, I mean the number of molecules in the asymmetric unit. The number of molecules in the asymmetric unit started in this case. All these are in crystal structures in the in situ cryocrystallization process of phenylacetylene. Again, a liquid at room temperature. So these studies essentially indicated that polymorphism is an issue which is still will make us shudder to ask questions. So we still have to be slightly afraid of what is polymorphism. Why it forms is a very big question. What is polymorphism is another question. So I come to the conclusion, having considered all aspects of polymorphism, attempts to obtain a single phase is a challenge. The subtle balance between thermodynamic and kinetic aspects is paramount. Crystal engineering methods are suggested but cannot universally be applied. Crystal structure prediction needs pruning. That is a big area of crystal structure prediction. A lot of people construct the so-called energy landscape, but it is very complex and varied, and there is not much of a success yet in this area. Polymorphism is a major headache issue in drug industry. It is desirable to create drugs which exist as a monomorph, and that is the requirement. Efforts to stabilize unstable polymorph is an issue which one has to discuss. How pure is the drug and what levels of impurities can be tolerated is the question which comes up when we took the example of Tadol. So we now reach a stage where I thought I will close the talk by giving a statement from the Lord of the Rings, as mentioned by Tolkien. The road goes on ever on and on, down from the door where it began. Now far ahead the road has gone, and I must follow, if I can, pursuing it with weary feet, until it joins some larger way where many paths and errands meet. And whither then, I cannot say. And this is where we are with polymorphism. Thank you very much, and I acknowledge my students, postdocs, project assistants, and the funding from DST. And currently, I'm an IAC senior scientist. Thank you very much.
Fabulous. Thank you very much, Guru. Stimulated several questions, and I think what we'll do for time purposes, maybe we'll take 2 questions, Guru, and then others will be able to answer offline, and we'll forward it to all of the attendees here. So let me pull up a couple here. And one is a general question: how is a co-crystal different from a solvate?
Okay. As I mentioned, that there was a meeting of several crystal engineering groups, which were asked by FDA to meet. In fact, the meeting was in India, New Delhi. And Zovarodko conducted this meeting. And there were lots of discussions on this issue. It's a very valid question. Solvates or with, let's say, hydrates or whatever, it's a solvent incorporated into the crystal lattice. And as a consequence, the solvent now modulates the formation of the crystal. So if we accept the solvatomorphs or the solvate-mediated pharmaceutical sample in a crystalline state, it is by definition an accepted fact. So there was a discussion what happens with co-crystals. In case of co-crystals, it's not a question of a solvent getting incorporated. In other words, we are not using the solution and then using the solvent. In the case of a hydride, we are using water. And crystallization is done using water as a medium. And as a consequence, water gets into the system and we get the hydrate form. In case of the co-crystals, it is also possible to have both of them in solid state. And there is a solid state reaction, just like the solid state reaction, which was illustrated to form a dimer in the case of the cinnamic acid. So the solid state reaction is an issue which comes in the case of co-crystals. And as a consequence, co-crystals therefore are different entities. So FDA at that particular time was not sort of ready to accept co-crystals as a possible polymorphic accepted form to become a drug. So co-crystals still remain an enigma. At the same time, it has been discovered, several literature studies show that co-crystals can also form polymorphs. And so the issue becomes more and more complicated. To answer the question in one line, co-crystals therefore are different from that of solvent or a salt.
Okay. All right, and maybe one more. We have several questions, and again, we'll get these answered offline and send them to the attendees. Maybe perhaps one more question, Guru. Sir, why is the melting point of the polymorphs different?
Okay. The polymorphs melting point are different mainly because, the process of melting is essentially to disengage the molecule in the solid state. So the molecules which are now held by intermolecular interactions in case of packing polymorphism, or the molecules which are held in the conformational polymorphism due to variations in the conformational arrangements, which essentially now produces the crystal. The two phases now dissolve. When we talk about dissolution, essentially what it means is that now the molecules are all separated out and they are free now. At that particular temperature, they go into different orientations, and therefore they have now freedom of rotation. So the molecule now starts to rotate. So at the melting point, therefore, they all separate. At that particular temperature, the molecules separate from the solid form and they go into a free state. And these are now able to rotate and move with Brownian motion. So they essentially can become either a liquid or a vapor, depending upon the nature of the solid, of course. You can have vaporization possible. And as a consequence, the melting points become different because they are differently held. And therefore, the strengths that are required to break the intermolecular interactions are different from each other. So energetically, they are different. And so as a consequence, different melting points will indeed mean that they are different polymers.
All right. All right, everybody. It is time to finish up for today. Very interesting presentations, and clearly additional questions are here, which says it was a very good, stimulating discussion, Guru. So first, let's thank you for the presentation. Excellent presentation. And I also like to thank the attendees for joining us today.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on ICDD.com. Contact us at info@icdd.com.